All right, guys, so we talked about the limit definition of the derivative by thinking of a secant line with a delta x that gets closer and closer to zero. What we're going to do now is put all these things together and actually try to apply it to a problem to find the derivative. So to recap, in the prior video we started here. We noticed that if we drew a secant line through a curve and we labeled it as you see on this coordinate plane, that we could use all that information to rewrite slope. Essentially, we wanted to get delta x, the distance between x and x plus delta x, to be closer and closer to 0. So if we do that, we can use the term, the limit as delta x goes to 0, of the average rate of change. Remember, this is just representing slope, but with that newer notation. What you can also see here is a curve where we're showing you delta x getting closer and closer to 0. Here's the curve first. And as you zoom in, notice it's still a secant line, still a secant line, still a secant line, but the distance is getting closer and closer to this point here where it's actually a curve with a tangent line. So that was the prior video, recapped with those pictures. The next question is, how do I actually use this? Now, yeah, we learned the power rule in the first class, and I explained to you guys how you could look at a function and with the power rule get the derivative. But where that all comes from is actually this limit definition of the derivative. So I do want you to practice a little bit of actually using Algebra 2 and some pre-calc to rewrite expressions this way to find the derivative. So let's take a look at what happened in this problem here. In this example, we start with g of x equals x squared minus 2x. Now, we already know through power rule that the derivative, g prime of x, should equal 2x minus 2. We know this because of the power rule. What I want you to do is use the limit definition of the derivative to prove that. And what you'll see here at the bottom of the page is I did prove it. I got 2x minus 2 from the limit definition, and we know from the power rule that is correct. But how did I get there? So let's look. First, we started with the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And we know that that means the derivative. So I used the correct notation. I said it equals f prime of x. So now I got to plug in that function. The function was 2x minus 2. When I plug in 2x minus 2, remember, f of x plus delta x, this, has to be rewritten. Meaning whenever there's an x, I have to say x plus delta x, right? But we're using x squared minus 2x. That's our original function. So when I try to plug that in, it's got to be x plus delta x squared minus 2, open parentheses, x plus delta x, which gives me this messy part right here, right? That's all of this. Over here, it's just minus f of x. So I just copy the function, x squared minus 2x, and we're good. Okay, so to recap, this first part is f of x plus delta x minus just the function f of x all over delta x. The rest is just algebra. So if you look here, you can check my algebra here. I did some work. The x squareds cancel out. The 2x delta x minus 2x delta x, that cancels out. All right, and we're left with what you see here in blue. 2x delta x plus delta x squared minus 2 delta x. So since there's a delta x in each of these, as we know in algebra, we can factor that out. So we factor that guy out, and lo and behold, we get the final step. The limit as delta x approaches 0 of 2x plus delta x minus 2. Well, as you get closer and closer to 0, let's see what happens if we plug this in. This is linear, so we can plug it in. So 2x plus 0 minus 2 leaves us with 2x minus 2. And there we go. G prime of x equals 2x minus 2. I'm going to show you two more examples here. You can freeze the video and check this out, but this problem was f of x equals x squared minus 9x plus 3. And I rewrote it first using the proper notation of f of x plus delta x. I simplified my work here in step 2. I show you how I'm breaking down the work by using like terms, canceling things out, and then my last step, I'm able to factor out delta x over delta x, giving me 2x plus delta x minus 9. When I do that, I am left with that final answer there. All right? So, overall, here's some things that I want you to capture from today's class and from the class yesterday, and a little bit of new information. When we get a tangent line to a curve, we can use that to get the slope of that curve at that point, and that will be called the derivative. The limit as delta x approaches 0, using the average rate of change with that notation, is also the definition of the derivative. There's an example here of finding the derivative. And don't forget, the day before, we talked about the connection between position, velocity, and acceleration, where the instantaneous rate of change of position is velocity, and the instantaneous rate of change of velocity is acceleration. While we're working on functions and looking at a lot of graphs, I want to leave you guys with remembering there's a few features of graphs that are really important for us to know. First, in this picture here, you can see that we're looking at a maximum, a minimum, and then you have this point here, which is called a cusp, where it almost comes to a point, right? So these are just different words that we're going to be using when we look at different functions in this class. And the last thing that I want you to write down, this is a really important fact, we use the phrase horizontal tangent to actually identify when a derivative equals 0. So I want you to make sure you pause this video and write down these new definitions that I've just introduced at the end of this course of lesson 2. So we've got maximum, minimum, cusp. And we also have the term horizontal tangent. And again, when we say horizontal tangent line, we mean the derivative is 0 when we have a horizontal tangent.